Now, in this lecture, we'll answer on two questions. The first question, we'll find out the radius of this circle that is inscribed by the right triangle ABC. And in the second question, we'll find out the area of the blue right triangle DCB that is inscribed by the quarter circle. We'll start with the first question. In the drawing, we have the right triangle ABC, side AB equals to 8 units, angle ABC, this angle equals to 90 degrees, and it is also given us in the question that the length of side BC and the length of side AC, those two lengths are integers, and our mission is to find out the radius of this circle that is described by the right triangle ABC. So first of all, we will define side BC as A, and we will define the hypotenuse AC as B. In the next step, we will implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, in the right triangle ABC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AB square plus BC square. We repeat again, the right triangle ABC, by PT is the equation for Pythagoras theorem, AC square equals to AB square plus BC square. According to our definition, AC equals to B, so AC square will be equal to B square and it is equal to AB square. AB equals to 8 units, so AB square is 8 squared, that is 64, plus BC square. BC equals to A according to our definition, therefore BC square will be equal to A square. So in conclusion, according to equation number 1, we found out that B square equals to 64 plus A square. We will subtract from this equation number 1 A square, and we get that according to equation number 1, B square minus A square equals to 64. Here we use the algebraic identity that B square minus A square, it is actually equals to B plus A times B minus A, so we substitute B square minus A square by B plus A times B minus A, and according to equation number 1, it is equal to 64. So actually, according to what is given us in the question, AC and BC are integers. That is to say, according to our definition, BC is A and AC is B. That is to say, A and B are integers. A and B are integers. That is the first thing that we know. And we also know that A and B are the lengths of the sides of the right triangle. So A and B, their lengths, and as lengths, they must be positive numbers. Okay, so here from 1 and 2, we will derive that A and B are positive integers. A and B are positive integers. So B is a positive integer and A is also a positive integer. Therefore, B plus A will be also a positive integer. Okay? So actually, B plus A must be greater than B minus A for the simple reason that when you add two positive integers to each other, the result always will be greater than the case that when you subtract them from each other. Therefore, B plus A must be greater than B minus A. And we also know that B is the hypotenuse and A is the perpendicular in the right triangle ABC. And we know that the hypotenuse is always greater than the perpendicular, so B is greater than A. B is greater than A. We subtract A from this inequality and we will get that B minus A is greater than 0. That is to say, B minus A is a positive number. So B is a positive integer, A is a positive integer, and if B minus A is a positive, it must be a positive integer. That is to say, B minus A, it is also a positive integer. I repeat again, because of the fact that B and A are both positive integers, it means that if you subtract one from the other, if the result is not a negative number, then it means that the result must be a positive integer. Okay? Actually, according to equation number 1, we have here two positive integers that we multiply each by each other, and when we multiply the two positive integers by each other, the result is 64. Actually, there are not a lot of possibilities that when you take two positive integers and multiply them by each other, the result will be 64. So we write down all the possibilities for two positive integers that you will multiply by each other, and the result will give us 64. The first couple will be 1 and 64. The second couple of positive integers will be 2 and 32. The first couple of positive integers will be 4 and 16. The fourth couple of integers will be 8 and 8. The fifth couple of integers will be 16 and 4. The sixth couple of positive integers will be 32 and 2. And the last couple of integers, of positive integers, will be 64 and 1. Those are the only 7 possibilities that we have, that if we take two positive integers and we multiply them by each other, the result will give us 64. But because of the fact that we actually proved that b plus a is greater than b minus a, it means that the first column, that is b plus a, must be greater than the second column, that is b minus a. So all the options that are not give us that the first column is greater than the second column, we will cancel them. It is not a good option because we have already proved that b plus a must be greater than b minus a. So we'll check out what are in which options the first column is greater than the second column, and only the options that give us that the first column is greater than the second column, those are the valid options for the solution of the question. So we start to check here. 1 is not greater than 64, that is not a good option. 2 is not greater than 32, that is not a good option also. 4 is not greater than 16, that is not a good option. 8 is not greater than 8, that is not a good option. 16 is greater than 4, that is to say it is a good option. 32 is greater than 2, that is a good option. And 64 is also greater than 1, that is also a good option. So we left only the 3 options that are left for our solution to the questions, those 3 options. And in the next step, we will add the two numbers together in order to find out the result of adding the two numbers together, and we'll get that b plus a plus b minus a, it is actually equals to b plus b, that is 2b, and a minus a is 0. So actually we found out that when we add the two numbers together, the two positive integers together, the result must be an even number. Why? Because 2b is an even number. Why 2b is an even number? Because b is a positive integer, and when you multiply a positive integer by 2, the result must be an even number. So we write it down that 2b is an even number. Therefore, we will add the two numbers to each other in the three options, and only the results that give us an even number will be valid for the solution to the question. Here 16 plus 4 is 20. 20 is an even number, therefore this is a good solution to the question. 32 plus 2 is 34. 34 is also an even number. It is also a good solution to the question. And 64 plus 1 is 65. It is not an even number. It is an odd number, so it is not a good solution. So we're left only with two possible solutions to the question. 16 and 4, and the second one is 32 and 2. So I'll write down the two solutions to the question. So the first option is that b plus a equals to 16. And b minus a equals to 4. The second option is that b plus a equals to 32, while b minus a equals to 2. Here we will focus on the first option, and we will add the equation number 1 to equation number 2, and we get that b plus b is 2b, a minus a plus minus a is a minus a, that is 0, and in the other side of the equation we have 16 plus 4, that is 20. So in conclusion, we got the equation that 2b equals to 20. We divide this equation by 2, and we get that b, the hypotenuse b, equals to 20 over 2, that is 10 units. So b equals to 10 units, and according to the first question, to the first equation, b plus a equals to 16. Here we subtract b from this equation, and we get that a equals to 16 minus b, and we already found out that b equals to 10, so we substitute b by 10 here, and we get that a equals to 16 minus b is 10, so it is 16 minus 10, and 16 minus 10 is 6. In conclusion, we found out that a equals to 6 and b equals to 10. That is to say, in the right triangle ABC, the perpendicular a is equal to 6 units, the other perpendicular equals to 8 units according to what is given as the question. And here I will draw the first solution. Here, according to the first solution to the question, it is given us in the question this is the right triangle ABC. Angle ABC equals to 90 degrees. It is given us the question that side AB equals to 8 units. We just right now found out that BC, that is A, it is equal to 6 units. And AC, that is B, the hypotenuse equals to 10 units. Inside this right triangle, triangle ABC, we have a circle that is inscribed. And our mission is to find out the radius of this circle. Okay, so we define the radius of this circle as capital R. And our mission is to find out the radius of this circle, but that is inscribed by this right triangle. And we have also the second solution. So here we will add equation number 1 to equation number 2, and we'll get that B plus B is 2B, A plus minus A is A minus A, that is 0. In the other side of the equation we have 32 plus 2 is 34. So in conclusion we found out that 2B equals to 34, we divide this equation by 2, and we get that B, the hypotenuse, equals to 34 over 2 is 17. We have the equation that B plus A equals to 32. We'll subtract B from this equation, and we get that A equals to 32 minus B, and B is 17, so we substitute B by 17, and we get that A equals to 32 minus B, that is 17. So A equals to 32 minus 17, that is 15. And B equals to 17. So according to the second option, we have here the right triangle, triangle ABC. In the right triangle, triangle ABC, angle ABC equals to 90 degrees. It is given us the equation that AB equals to 8 units. We just right now found out that BC, that is A, according to our definition, it is equal to 15 units. And the hypotenuse AC, that is equal to B, according to our definition, is equal to 17 units. Inside this right triangle, triangle ABC, we have a circle that is inscribed by the right triangle. And our mission is to find out the radius of this circle. Again, we define the radius of this circle as capital R. In the next step, we'll find out the radii of the two circles that are inscribed by those two right triangles, triangles ABC. Okay? So in order to find out the radii of the two circles that are inscribed in the right triangles, triangles ABC, on those two specific right triangles, we will take a right triangle, triangle ABC, that could be any right triangle. Inside this right triangle we have this circle. We will find out the radius of this circle, and we will use the formula that we will find in order to find out the radii of the two right triangles that we have here, the radii of those two right triangles, in order to find out the radii of those two circles that are inscribed in those two right triangles. And the reason that we can use the formula that we will find for the radius of this circle that is inscribed by triangle ABC is because of the fact that here triangle ABC could be any right triangle, and especially triangle ABC could be those two right triangles. Okay, so here we'll take triangle ABC that could be any triangle, any right triangle. That is to say, here side AB of the right triangle ABC is equals to A, side BC of the right triangle ABC equals to B, and side AC, the hypotenuse AC of the right triangle ABC equals to C according to our definition. We will define the center of this circle as O. The radius is equal to capital R. We will define the point of tendency of tangent AB with this circle as N. We will join points N and O together by a straight line. Point O is the center of the circle. Point N is the point on the circle itself. This is exactly the definition of a radius. That is to say, line segment NO is the radius of this circle that is equal to capital R according to our definition. We will define the point of tendency of tangent BC with this circle as M. We will define the point of tendency of tangent AC with this circle as L. So here we have rule number 1 that says that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius ON that is drawn to the point of tendency. The radius ON, it is drawn to the point of tendency, that is to say, it is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be equal to 90 degrees according to rule number 1. Likewise, we have here the radius OM that is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then according to rule number 1, tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So actually, here in quadrilateral ONBM, we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 200 70 degrees, plus the size of the fourth angle, that is actual angle NOM. In total, the sum of those four angles, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, so 270 degrees plus the size of angle NOM, it is equal to 360 degrees. If we subtract 270 degrees from the equation, we get that the missing angle NOM equals to 90 degrees. So actually found out that inside quadrilateral NOBM we have four right angles. Any quadrilateral that has four right angles must be at least a rectangle if not a square. So we relate to quadrilateral NOBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. NO equals to BM, but NO itself equals to R. And it is also equals to BM, therefore BM also will be equal to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. OM equals to NB, but OM equals to R. And it also equals to NB, therefore NB also will be equal to R. So we found out that in quadrilateral NOBM, all of its sides are equal to each other, they are equal to R, therefore quadrilateral NOBM, it is not a rectangle but a square. We find out the length of AN. Here AN equals to AB minus NB. Again, AN equals to AN equals to AB, that is A, minus NB, that is R. So in conclusion, we found out that AN equals to A minus R. Likewise, we find out the length of line segment MC. From the drawing, it is very easy to see that MC equals to BC minus BM. That is to say, MC equals to BC, that is B, minus BM, that is R. So in conclusion, MC equals to B minus R. And we have also rule number 2 that states that the lengths of two tangents from the common external point to a circle are equal. So here, if we focus on the common external point, point A, from the common external point A, we have two tangents to this circle, tangent AN and tangent AL. And according to rule number 2, they are equal to each other. That is to say, AN equals to AL. AN equals to AL according to rule number 2. But we have already found out that AN equals to A minus R. And it is also equal to AL, so therefore AL will be also equal to A minus R. Likewise, if we focus on the common external point, point C, from the common external point C, we have two tangents to this circle, tangent CL and tangent CM. And according to rule number 2, they are equal to each other. That is to say, CL equals to CM. CL equals to CM according to rule number 2. But we have only found out that CM equals to B minus R, and it is also equals to CL. Therefore, CL will be also equal to B minus R. So in conclusion, we found out that the hypotenuse AC, it is equal to AL plus NC, it is equal to AL, that is A minus R, plus NC, that is B minus R. So I write it down. So the hypotenuse AC, for drawing, you can see that the hypotenuse AC equals to AL plus LC. But AC equals to C according to our definition. So we substitute AC by C. AL equals to A minus R, according to what we have already found out. So we substitute AL by A minus R. and LC equals to B minus R according to what we have already found out. So we substitute LC by B minus R. So in conclusion, we found out that according to this equation, C equals to A minus R plus B minus R. So C equals to A plus B minus R plus minus R is minus 2R plus minus 2R. Here we add 2R to this equation and we get that 2R plus C equals to A plus B. Here we subtract C from this equation and we get that 2R equals to A plus B minus C. Here we divide this equation by 2 and we get that R, the radius that we are looking for, it is equal to A plus B minus C over 2. So we found out the radius of this circle that is inscribed by triangle ABC that could be any triangle. And because of the fact that the right triangle, triangle ABC, could be any right triangle, we can use the formula that we found in order to find out the radii of those two circles that are inscribed by those two right triangles. Okay, actually, the formula that we found for the radius of the circle that is inscribed by triangle ABC that could be any triangle is equal to A plus B, that is the sum of the perpendiculars, minus C, that is minus the hypotenuse, over 2. Now we'll use this new formula in order to find out the radius of this circle that is inscribed by the right triangle, triangle ABC, because as I've already mentioned, triangle ABC, the right triangle, triangle ABC could be any right triangle, and especially it could be this right triangle and also this right triangle. So here R equals to A plus B is the sum of its perpendiculars, that is 8 plus 6 minus the hypotenuse, that is 10 over 2. 8 plus 6 equals to 14 minus 10 over 2. So R equals to 14 minus 10 is 4 and 4 over 2 is 2. So we found out that the radius of this circle that is inscribed by this right specific triangle equals to 2 units. R is equal to 2 here. Then we find out the radius of this circle that is inscribed by this right triangle. According to the new formula that we found, the radius equals to the sum of its perpendiculars, that is 8 plus 15 minus the hypotenuse, that is 17 over 2. 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So here R equals to 3 units. So in conclusion, we have two solutions to the question. Here, the radius of this circle that is inscribed by this specific right triangle, triangle ABC, which will be equal to either 2 units or 3 units. Okay, and that is the answer to the question. Okay, so we finished with the first question. In the next step, I will present to you the second question, and We will solve the second question in two different methods. In the drawing, we have this quarter circle. Side OB equals to 2 units. AD equals to DO. Inside this quarter circle, we have the right blue triangle, triangle DCB. And we want to find out the area of this right blue triangle, triangle DCB. So we start with the first method. AOB is a quarter circle. That is to say, angle AOB must be equal to 90 degrees. Point O is the center of the quarter circle. And the radius of the quarter circle equals to 2 units. And we know that AD equals to DO. So if AD equals to X, then DO will be also equal to X. AO is also the radius of the quarter circle, that is equal to 2 units according to what is given as the question. So here AD plus DO equals to AO. AD plus DO equals to AO. But AO is the radius of the quarter circle, that is also equals to OB. And it is equal to 2 units according to what is given as the question. Okay, so AD plus DO is AO, and AO equals to OB. And OB is the radius of the quarter circle, that is equal to 2 units. Here AD is X according to our definition, and DO is also X according to our definition. So AD plus DO is X plus X. X plus X is 2X. And according to this long equation, 2X equals to 2. We divide this equation by 2 and we get that X equals to 1 unit. So here X equals to 1 unit. So you can write down that AD that is equal to X, it is actually equals to 1 unit. And DO that is also equals to X, it is equal to 1 unit. In the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle, and we'll extend the radius BO by a straight line until it touches the circle at this point. We will define the touching point of the extended BO in the circle as point P. Here point O is the center of the circle, and point P is the point of the circle itself. This is exactly the definition of a radius. That is to say, PO is the radius of this circle, that is equal to 2 units, because the radius of the circle is the same radius as the radius of the quarter circle, that is equal to 2 units. Okay? In the next step, we will extend side CD by a straight line until it touches the circle. And we actually don't know at which point the extended CD will touch the circle. So we'll assume that the touching point of the extended CD with this circle will be at this point, point X. According to our assumption, when we extend side CD by a straight line, it will touch the circle at this point, point X. So actually, with this construction, we created peripheral angle BCX. Here we have the peripheral angle BCX. and peripheral angle BCX equals to 90 degrees according to what is given as the question. Okay, we know that peripheral angle BCX is equal to 90 degrees. It is given as the question that this angle equals to 90 degrees, therefore peripheral angle BCX equals to 90 degrees. What is the definition of segment line PB? Segment line PB is a straight line because we extended the radius BO by a straight line and we created PB. Therefore PB is a straight line. It is a chord that passes for the center of the circle, that is to say it passes for point O, and therefore any chord that passes for the center of the circle is defined as the diameter of the circle. So PB is the diameter of the circle, and according to the rule that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, it means that peripheral angle BCX, this peripheral angle that is equal to 90 degrees, must rest on the diameter of the circle, but the diameter of the circle is PB. And you can see from the drawing that peripheral angle BCX is not resting on the diameter PB, but it is on BX. So we have here a contradiction because we have here peripheral angle BCX that is equal to 90 degrees, and still it is not resting on the diameter of the circle that is PB. So in order to solve the contradiction, we must conclude that point X merges with point P, and when point X merges with point P, will not have any contradiction. Here when point X merges with point P, we have here peripheral angle BCP that is equal to 90 degrees, and it does rest on the diameter of the circle that is PB. Okay, so that is to say peripheral angle BCX that is equal to 90 degrees, it is actually equal to peripheral angle BCP. Why? Because point X merges with point P. In this way, we have peripheral angle BCP that is equal to 90 degrees, and it rests on the diameter of the circle that is PB. Okay? So PB is the diameter of the circle, therefore it is absolutely a straight line. And we know that the sum of the angles on one side of a straight line equals to 180 degrees, so if we focus on the upper side of the straight line PB at point O, here the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have on the upper side of PB at point O? We have here 90 degrees plus angle AOP. In total, the sum of those two angles must be equal to 180 degrees. So 90 degrees plus angle AOP equals to 180 degrees. If we subtract 90 degrees from the equation, we get that the missing angle AOP equals to 90 degrees. Okay? So we have here the right triangle POD. In the right triangle POD, by PT is the relation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, PD square equals to DO square plus PO square. I repeat again, in the right triangle, triangle POD, PD square equals to DO square plus PO square. So PD square equals to DO square. DO equals to 1, so DO square is 1 square, that is 1, plus PO square. PO equals to 2, therefore PO square is 2 square, that is 4. So in conclusion, we found out that PD square equals to 1 plus 4, that is 5. Here we take out of this equation and we get that the hypotenuse PD equals to the square root of 5 units. Okay, PD equals to the square root of 5 units. I see that PD equals to the square root of 5 units. We repeat on the same process of the right triangle, triangle ODB. In the right triangle, triangle ODB by PT. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say DB square equals to DO square plus OB square. I repeat again, in the right triangle, triangle DOB, according to the Pythagoras theorem, PB square equals to DO square plus OB square, so DB square equals to DO square. DO equals to 1, so DO square is 1 square, that is 1, plus OB square. OB is 2, so OB square is 2 square, that is 4. So in conclusion, we found out that DB square equals to 1 plus 4, that is 5. We take out of this equation and we get that the hypotenuse DB equals to the square root of 5 units. Okay, here the hypotenuse DB equals to the square root of 5 units. In the next step, we'll extend the radius AO by a straight line until it touches the circle. At this point, we'll define the touching point of the extended AO on the circle as point Z. In the next step, I will present to you rule number 1, and we will implement rule number 1 in our drawing. Rule number 1 deals with two chords that intersect with each other inside the circle. So we have this circle. And this is rule number 1. Here, chord AB, this is chord AB, that intersects with chord CD, this is chord CD, and the intersection point between chord AB and chord CD is at point O. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. I'll repeat again on rule number 1. We have chord AB that intersects with chord CD at point O. Therefore, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Actually, we can implement rule number 1 in our drawing. Why? Because in our drawing we have chord AZ that intersects with chord CP at point D. Again, chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we'll get that AD times DZ equals to CD times DP. Repeat again. Chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ equals to CD times DP. AD times DZ equals to CD times DP. Here AD, actually here, what is the length of line segment OZ? O is the center of the circle, Z is the point of the circle itself. This is exactly the definition of a radius. That is to say, OZ is the radius of this circle that is equal to 2 units. Okay, so here AD equals to 1 unit. DZ, from drawing is very easy to see that DZ equals to 1 plus 2, that is 3. And it is equal to CD. CD is the missing line segment times DZ. CD times DP. CD is the missing line segment, so we leave it as it is, and DP it is equal to square root of 5 units. So in conclusion, we found out that 3 equals to CD times square root of 5 units. Here we will divide this equation by square root of 5 units, and we will get that CD equals to 3 over square root of 5 units. CD equals to 3 over square root of 5 units. Found out that CD, the missing line segment CD equals to 3 over square root of 5 units. In the next step, we'll implement the Pythagoras theorem on the right triangle, the right blue triangle CDB, and we find out the missing side CB. Okay. So in the right triangle, the right blue triangle CDB, by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say dB square, that is the square of the hypotenuse, equals to CD square plus CB square. And read again, in the right triangle CDB, according to the Pythagoras theorem, dB square equals to CD square plus CB square. So here, dB equals to square root of 5, so dB square is square root of 5 squared, that is 5. That is equal to CD square. CD is 3 over square root of 5, so CD square is 9 over 5. And CB is the missing side, so we leave it as it is. So in conclusion, we found out that 5 equals to 9/5 plus CB squared. Here we'll subtract 9/5 from this equation and we'll get that 5 minus 9/5 equals to CB squared. Here we'll multiply 5 by 5 and then we'll divide it by 5 in order to overcome the factor of this expression. 5 times 5 is 25 minus 9 over 5, it is equal to CB squared. So here we have 25 minus 9 is 16 and 16 over 5 equals to CB squared. We take out of this equation and we get that side CD, the missing side CB, it is equal to square root of 16, that is 4 over square root of 5. So here we found out that CB equals to 4 over square root of 5. Now it is very easy to find out the area of this right blue triangle, triangle CDB. The area of the right blue triangle, triangle CDB. Will be equal to the base of the triangle that is CD times the height to the base that is CB over 2. We repeat again, the area of the right blue triangle, triangle CDB will be equal to the base of the triangle that is DC times the height to the base that is CB over 2. Here DC equals to 3 over square root of 5. CB equals to 4 over square root of 5. All divided by 2. So 3 times 4 is 12. So in the numerator we have 12. In the denominator we have square root of 5 times square root of 5, that is 5 times 2. Here 12 over 2 is 6. So in the numerator we left only with 6. In the denominator we left only with 5. In conclusion, the area of the right blue triangle, triangle CDB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, we finished with the first method. In the next step I will present to you the second method. According to the first method, we have already found out that AD equals to 1 unit, DO equals to 1 unit, the radius of this quarter circle equals to 2 units, the center O is the center of the quarter circle, and here in the second method we'll complete the quarter circle to a circle. And we'll define the touching point of the extended radius OB in the semicircle is point P. In the first method we have already found out that angle AOP equals to 90 degrees. Actually those two angles, angle AOB equals to 90 degrees. According to the first method, and angle AOB, also, angle AOP, this angle also equals to 90 degrees. And the point O is the center of the semicircle, and point P is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, PO is the radius of the semicircle that is equal to 2 units, according to what is given as the question, because of the fact that the radius of the semicircle is the same as the radius of the quarter circle that is equal to 2 units. We'll extend side CD by a straight line until it touches the circle, and according to the first method, we've already proved that when we extend side CD by a straight line, it must touch the circle or the semicircle at point P. Okay? In the next step, we define angle DPO of the right triangle. DPO is theta. So angle DPO equals to theta. Angle DOP equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle 280 degrees. This angle equals to 90 degrees. This angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. And exactly for the same reason, if we focus on the right triangle BCP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, for the same reason that this angle must be also equal to 90 degrees minus theta. In the next step, we will prove that the right big triangle, triangle PCB, is similar to the right small triangle, triangle PDO. Okay? So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So angle POD, this angle, it is equal to this angle that is actually angle PCB, and they are both equal to 90 degrees, therefore they are equal to each other. I repeat again, angle POD equals to angle PCB equals to theta, and therefore they are equal to each other. So here, in addition, we have those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So that is to say, angle PDO, this angle equals to angle PBC, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. Repeat again. Angle PDO equals to angle PBC, and it is equal to 90 degrees minus theta. And finally, this angle is a common angle that belongs to both triangles, therefore this angle equals to itself. So angle DPO equals to angle CPB, the same angle, the angle equals to itself. So angle CPB, and it's equal to theta, so here angle DPO equals to angle CPB equals to theta. It is a common angle that belongs to both triangles. Actually, we proved that all the angles of triangle PDO can go into all the angles of triangle PCB, therefore triangle PDO is similar, this is the sign of similar, to triangle PCB according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it is equal also to PO over PC. I repeat again, from the fact that the two right triangles are similar to each other, we conclude that PD over PB equals to DO over CB equals to PO over PC. Here, according to the first method, we have already found out that PD, the hypotenuse PD equals to the square root of 5 units, and also the hypotenuse DB of the right triangle DOB also equals to square root of 5 units. Okay, so actually here PD equals to the square root of 5 units according to the first method over PB. PB is 2 plus 2, that is 4. DO, it is actually DO equals to 1 unit over CB. CB is the missing side, so we'll leave it as it is. And it is equal to PO. PO equals to 2 units over PC. PC equals to square root of 5 plus DC. So, in conclusion, I found out that square root of 5 over 4 equals to 1 over CB, and it is also equals to 2 over square root of 5 plus DC. From this long equation, we derive the first equation, the square root of 5 over 4 equals to 1 over CB. Here we cross multiply this equation number 1, and we get that according to equation number 1, square root of 5 times CB equals to 4. Here we divide this equation number 1 by square root of 5, and we get that CB equals to 4 over square root of 5. Here we found out that CB equals to 4 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. So the right blue triangle, triangle DCB, by PT, a relation from Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say dB squared equals to CB squared plus DC squared. Repeat again, in the right triangle DCB, according to the Pythagoras theorem, dB squared equals to CB squared plus DC squared. So dB squared equals to CB squared. CB equals to 4 over square root of 5, therefore CB squared will be equal to 16 over 5 plus DC squared. This is the missing line segment, so we'll leave it as it is. So in conclusion, we found out that dB squared equals to 16 over 5 plus DC squared. dB equals to square root of 5, therefore dB squared is square root of 5 squared, that is 5. So 5 equals to 16 fifths plus DC squared. Okay. 5 equals to 16 fifths plus DC squared. We subtract 16 fifths from this equation, and we get that according to this equation, 5 minus 16 fifths equals to DC squared. So here we multiply 5 by 5 and then we divide it by 5 in order to overcome a factor of this expression. 5 times 5 is 25 minus 16 over 5 equals to DC squared. Twenty-five minus 16 is 9, so 9 fifths equals to DC squared according to this equation. We take a root of this equation and we get that DC equals to the square root of 9, that is 3, over square root of 5. In conclusion, we found out that DC equals to 3 over square root of 5. Now it is very easy to find out the area of this blue right triangle, triangle DCB. The area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. I repeat again, the area of the blue right triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height of the base, that is CB, over 2. Okay, here. DC equals to 3 over square root of 5. CB equals to 4 over square root of 5. All divided by 2. So here 3 times 4 is 12. So in the numerator we left only with 12 over, in the denominator we have square root of 5 times square root of 5, that is 5 over 2. 12 over 2 is 6, so in the numerator we left only with 6, and in the denominator we left only with 5. So in conclusion, we found out that the area of the right blue triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. We finished with the second method. In the next step we will summarize the lecture. We'll start with the first question, of course. So, in the drawing, we have triangle, the right triangle, triangle ABC. Side AB equals to 8 units, angle ABC equals to 90 degrees. And we know that the lengths of BC and AC are integers. And we want to find out the radius of this circle that is described by this right triangle, triangle ABC. So first of all, we define side BC as A, side AC as B, and we implemented the Pythagoras theorem on the right triangle, triangle ABC. According to the Pythagoras theorem, AC square equals to AB square plus BC square. In the right triangle, triangle ABC, AC square equals to AB square plus BC square. AC equals to B, so AC square is B square. AB is 8, so AB square is 8 squared, that is 64. BC equals to A according to our definition, therefore BC square is A squared. So in conclusion, according to equation number 1, B square equals to 64 plus A squared. We subtracted A squared from this equation, equation number 1, and we found out that B squared minus A squared equals to 64. We used here the algebraic identity that B squared minus A squared equals to B plus A times B minus A, and we substitute B squared minus A squared by B plus A times B minus A. And according to equation number 1, this is equal to 64. Here we know that AC and BC are integers according to what is given as the equation, but AC equals to B according to our definition and BC equals to A according to our definition. That is to say, A and B are integers according to what is given as the equation. And we also know that A and B are the lengths of the sides of the right triangle. So A and B as lengths, they must be positive numbers. So from 1 and 2, we'll get that a and b are positive integers. So if a and b are positive integers, it means that b plus a must be greater than b minus a. Why? Because when you add two positive integers to each other, the result will be always greater than the case that you subtract them from each other. So b plus a must be greater than b minus a, and b is a positive integer, a is a positive integer, so b plus a must be also a positive integer. And here we know that b is the hypotenuse. According to our definition, b is the hypotenuse of the right triangle in BC. Therefore, the hypotenuse is always greater than the perpendiculars. That is to say, b is greater than a. We subtracted a from this inequality, and we note that b minus a is greater than 0. That is to say, b minus a is a positive number. But because of the fact that b is a positive integer and a is also a positive integer, it means that b minus a, if it is a positive number, it must be a positive integer. Okay, so in conclusion, found out that b minus a it is also a positive integer. So b plus a is a positive integer, and b minus a is also a positive integer, and we know that b plus a is greater than b minus a. That is one thing, but we actually can say that when we multiply one positive integer, that is b plus a, in another positive integer, that is b minus a, the result must be 64. And then we wrote down all the possibilities that the multiplication of two positive integers by each other will give us the result of 64. So all the possibilities are 1 and 64, 2 and 32, 4 and 16, 8 and 8, 16 and 4, 32 and 2, and 61 and 4. So we have 7 possibilities that the multiplication of two positive integers by each other will give us 64. But because of the fact that we have already found out, we already proved that b plus a is greater than b minus a, it means that the first column, that is b plus a, must be greater than the second column, that is b minus a. So for us, the only valid options will be when the first column is greater than the second column. Otherwise, it is not a good option for us because we have already found out that b plus a must be greater than b minus a. So we check in which case we get that the first column is greater than the second column. If 1 is not greater than 64, that is to say it is not a good option. 2 is not greater than 32, 4 is not greater than 16, 8 is not greater than 8. All those options are invalid options. And we found out here 16 is greater than 4, that is to say it is a good option. 32 is greater than 2, this is also a good option. And finally 64 is greater than 1, therefore this is also a good option. So we have 3 possibilities for the answer to the question. In the next step, we added the two numbers together in order to find out the result. Here b plus a plus b minus a is b plus b is 2b, a minus a is 0. So in conclusion, when we add the two numbers together, the result must be an even number. Why? Because 2b is an even number. b is a positive integer, therefore 2b must be an even number. So we'll check all the 3 possibilities that we have here, and only if the addition of the two numbers together will give us an even number, it will be a good possibility. Otherwise we'll cancel these possibilities. So here 16 plus 4 is 20, and 20 is an even number, so it is a good possibility. 32 plus 2 is 34, that is an even number also, this is also a good possibility. And finally 64 plus 1 is 65, 65 is not an even number, it is an odd number, therefore it is not a good possibility because the addition of the two numbers together must give us an even number. So we left only with two options that are possible here for b plus a and b minus a. Okay, and so I wrote down the two options here. So according to the first option, b plus a equals to 16 and b minus a equals to 4, and according to the second option, b plus a equals to 32 and b minus a equals to 2. We focus on the first option and we will add equation number 1 to equation number 2, and we will get that b plus b is 2b, a minus a is 0. On the other side of the equation we have 16 plus 4, that is 20. So we got the equation that 2b equals to 20, we divided this equation by 2, and we got that b equals to 20 over 2, that is 10. So we found out that the equation b equals to 10 units. Then we have the equation that b plus a equals to 16. We subtracted b from this equation, we found out that a equals to 16 minus b, and b equals to 10 units, so we can substitute b by 10. So a equals to 16 minus b, and b is 10, so a equals to 16 minus 10, that is 6. So in conclusion, we found out that a equals to 6 units and b equals to 10 units. And according to the second option, b plus a equals to 32 and b minus a equals to 2, we added the two equations together to each other. So b plus b is 2b and a minus a is 0, and 32 plus 2 is 34. So in conclusion, we found out that 2b equals to 34. We divided this equation by 2 and found out that b equals to 34 over 2 is 17. So b equals to 17 units, and we have the equation that b plus a equals to 32. We subtracted b from this equation and found out that a equals to 32 minus b, but b equals to 17, so we can substitute b by 17, and found out that a equals to 32 minus 17, that is 15. So we found out that a equals to 15 and b equals to 17. Then I drew the two options that we have here. According to the first option, we have here the right triangle, triangle ABC. Angle ABC equals to 90 degrees. Side AB equals to 8 units according to what is given as the question. And we just right now found out that BC, that is A, according to our definition, it is equal to 6 units. And AC, that is B, equal to 10 units. So inside this right specific triangle, triangle ABC, we have this circle that is inscribed by this triangle ABC. And our mission is to find out the radius of this triangle, the radius of this circle. Okay, and we also have a second option for the right triangle, triangle ABC. Again, AB equals to 8 units, angle ABC equals to 90 degrees. According to what is given as the question, side BC that is equal to A, it is equal to 15 units, and side AC that is equal to B, it is equal to 17 units. So inside this right specific triangle, we have a circle that is inscribed, and our mission is to find out the radius of this circle. In order to find out the radius of the circle, we actually drew a right triangle, triangle ABC that could be any right triangle, and here, therefore, side AB will be equal to A units, side BC equals to B units, and side AC equals to C units. So we will find out the radius of this circle that is inscribed by this right triangle, triangle ABC that could be any right triangle, and by finding out the radius of this circle, we can implement this formula in order to find out the radii of those two circles that are inscribed by those two right triangles. Why you can use this formula? Because here we draw triangle, the right triangle, triangle ABC that could be any right triangle. This triangle, the right triangle, triangle ABC could be any right triangle, and especially it could be those two right triangles. Therefore, we can implement the new formula that we will find in those two right triangles. We can use them in those two right triangles because triangle ABC, the right triangle ABC could be any right triangle. Okay, so here, according to definition, side AB equals 2 units, side BC equals to B units, and side AC equals to C units. We define the center of the circle as point O. We define the point of tendency of tangent AB with this circle as N. Then we join points N and O together by straight line. Point O is the center of the circle, point N is the point of the circle itself. Therefore, NO is the radius of the circle that is equal to capital R. We define the point of tendency of tangent BC with this circle as M. And we define the point of tendency of tangent AC with this circle as L. Then, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius ON that is drawn to the point of tendency. Therefore, tangent AB will be perpendicular to radius NO according to rule number 1. So if AB is perpendicular to NO, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we have here the radius OM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent BC in this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. So if BC is perpendicular to MO, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. So actually inside quadrilateral NOBM we have 1, 2, 3 right angles. 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle that is actually angle NOM. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees. So 270 degrees plus the size of angle NOM must be equal to 360 degrees. If you subtract 270 degrees from the equation, we get that the missing angle NOM equals to 90 degrees. Therefore, inside quadrilateral NOBM we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral NOBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other, that is to say NO equals to VM. NO equals to VM, but we have already found out that NO equals to R, and it is also equals to BM, therefore BM also equals to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that NB equals to OM. For one side, NB equals to OM. From the other side, we have already found out that OM equals to R. And OM equals to also to NB. Therefore, NB also must be equal to R. So in conclusion, in quadrilateral NOBM, we have all of its sides are equal to each other, they are equal to R. Therefore, quadrilateral NOBM, it is not a rectangle but a square. Then we found out the length of side AN. Side AN equals to AB minus NB. Again, AB minus NB equals to AN. That is to say, AN equals to AB, that is A, minus NB, that is R. In conclusion, AN equals to A minus R. Then we found out the length of line segment MC. From the drawing, it is very easy to see that MC equals to BC minus BM. BC is B and BM is R, so BC minus BM is B minus R. So MC equals to B minus R and AN equals to A minus R. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So if we focus on the common external point A, from the common external point A, we have two tangents to this circle, tangent AN and tangent AL. And according to rule number 2, AN must be equal to AN. AN equals to AN according to rule number 2, but we have already found out that AN equals to A minus R. And it is also equals to AN according to rule number 2. Therefore, AL also must be equal to A minus R. Then we focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CM and tangent CL. And according to rule number 2, they must be equal to each other. That is to say, CL equals to CM. So from one side, CL equals to CM. But from the other side, we have already found out that CM equals to B minus R. So CM equals to B minus R, and it is also equals to CL. Therefore, we can conclude from it that CL is also equals to B minus R. So in conclusion, CL equals to B minus R, and AL equals to A minus R. So what is the length of the hypotenuse AC? The hypotenuse AC equals to AL plus LC. Again, the hypotenuse AC equals to AL plus LC. So the hypotenuse AC equals to AL plus LC. So AL equals to A minus R, and LC equals to B minus R. So we substituted AL by A minus R and LC by B minus R, and AC equals to C according to our definition. So we substituted AC by C. So in conclusion, we found out that C equals to minus R plus B minus R. That is to say, C equals to A plus B minus R is minus 2R. So C equals to A plus B minus 2R. We added 2R to this equation. We found out that 2R plus C equals to A plus B. We subtracted C from this equation. We found out that 2R equals to A plus B minus C. We divided this equation by 2 and found out that R, the radius of the circle that we are looking for, it is equal to A plus B minus C over 2. Okay, here the radius of this circle, it is equal to A plus B, that is the sum of the perpendiculars of the right triangle ABC, minus the hypotenuse, that is C over 2. And because of the fact that the right triangle ABC could be any right triangle, we can implement this formula in our two specific right triangle, because the right triangle ABC could be any right triangle. Okay, so we implemented the new formula in our two right triangles, those two right triangles. We have the formula that R equals to A plus B minus C over 2. That is to say, it is equal to the sum of the perpendiculars of the right triangle minus the hypotenuse over 2. Here, in this right triangle ABC, A is 8, B is 6, so it is 8 plus 6, that is 14, minus the hypotenuse, that is C, is 10 over 2. So 8 plus 6 is 14, and 14 minus 10 is 4, and 4 over 2 is 2. So in conclusion, found out that the radius of this circle that is described by this specific right triangle equals to 2 units. Then we found out the radius of this circle according to the new formula. This is equal to the sum of the perpendiculars of the right triangle ABC. That is to say, it is 8 plus 15, that is 23, minus the hypotenuse, that is 17 over 2. 23 minus 17 is 6, and 6 over 2 is 3. So the radius of this circle equals to 3 units. In conclusion, the answer to the question is that the radius of this circle that is described by this specific right triangle ABC equals to either 2 units or 3 units. Here the radius of this circle equals to either 2 units or 3 units. We finished with the first question, then I presented to you the second question. We solved the second question in 2 different methods. In the second question, we have a quarter circle, side OB equals to 2 units, AD equals to DO. Inside this quarter circle, we have the right blue triangle, triangle CBD, and we want to find out the area of this right triangle, triangle CBD. Okay, so first of all, because of the fact that A or B is a quarter circle, point O is the center of the quarter circle, OB is the radius of the quarter circle that is equal to 2 units, AO also equals to 2 units, it is also the radius, and here AD equals to DO, so if AD is X, then DO is also X, and AO equals to AD plus DO. Here, from the drawing it is very easy to see that AO equals to AD plus DO. So if AD equals to X, then DO must be also equal to X because they are equal to each other. So X plus X is 2X, and AO equals to OB equals to the radius of the quarter circle that is equal to 2 units. From this long equation, we will derive that 2x equals to 2. We divided this equation by 2 and found out that x equals to 1 unit. So here, AD that is equal to x equals to 1 unit, and DO that is also equals to x, this is also equals to 1 unit. Then we completed the quarter circle to a circle, and we extended side BO until it touches the circle at point P. Point P is the touching point of the extended BO and the circle. Point O is the center of the circle, point P is a point of the circle itself. This is exactly the definition of a radius, that is to say PO is the radius of this circle that is equal to 2 units. Then we extended side CD by a straight line until it touches the circle, and we assume that it touches the circle at point X. This point X. Okay, we assume that side CD will touch the circle, the extended side CD will touch the circle at this point X. Okay, so we actually created here peripheral angle BCP, that according to what is given as the equation, it is equal to 90 degrees, and it doesn't rest on the diameter of the circle, that is PB. PB is the diameter of the circle because of the fact that it passes for point O, that is the center of the circle. So we have here a contradiction because we have here peripheral angle BCX that is equal to 90 degrees, and although that is equal to 90 degrees, it still doesn't rest on the diameter of the circle, that is PB. And we know that any peripheral angle that is equal to 90 degrees must rest on the diameter. So we have here a contradiction. In order to solve the contradiction, we must assume that point X merges with point P, and here we have the peripheral angle PCB that is equal to 90 degrees, and peripheral angle PCB indeed rests on the diameter of the circle, that is PB. So here, peripheral angle BCX that is equal to 90 degrees, it is equal to peripheral angle BCP because point X merges with point P. Okay? Then PB is the diameter of the circle, that is to say it is absolutely a straight line. And we know that the sum of the angles on one side of a straight line equals to 180 degrees. So if we focus on the upper side of the straight line PB at point O, the sum of the angles must be equal to 180 degrees. So which angles we have on the upper side of PB at point O? We have 90 degrees plus angle AOP. In total, the sum of those two angles must be equal to 180 degrees. If we subtract 90 degrees from the equation, we will get that this angle equals to 90 degrees. So then we have here, we created here the right triangle PDO. We implemented the Pythagoras theorem here. According to the Pythagoras theorem, PD square equals to OD square plus PO square. In the right triangle POD, according to the Pythagoras theorem, PD square equals to PO square plus PD square equals to DO square plus PD square. So PD squared equals to DO squared. DO is 1, so DO squared is 1 squared, that is 1. PO squared. PO is 2, so PO squared is 2 squared, that is 4. So PD squared equals to 1 plus 4, that is 5. We took out of this equation and found out that PD equals to the square root of 5 units. Here the hypotenuse PD equals to the square root of 5 units. We repeated on the same process on the right triangle DOB. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say dB squared equals to DO squared plus OB squared. In the right triangle DOB, dB squared equals to DO squared plus OB squared. That is to say dB squared equals to DO squared. DO equals to 1, so DO squared is 1 squared, that is 1, plus OB squared. OB is 2, so OB squared is 2 squared, that is 4. So we found out that dB squared equals to 1 plus 4, that is 5. We took out of this equation and found out that the hypotenuse dB equals also to the square root of 5 units. Then we implemented rule number 1 in our drawing. In our drawing, we have, according to rule number 1, if we have this circle, inside this circle we have chord AB, that is the section chord CD at point O, then AO times OB equals to CO times OD, again AO times OB equals to CO times OD. We can implement rule number 1 in our drawing, because in our drawing we have chord AZ, that intersects with chord PC at point D. Here chord AZ intersects with chord CP at point D, therefore according to rule number 1, AD times DZ equals to CD times DP. Again, AD times DZ equals to CD times DP. AD equals to 1. Here, DZ equals to 1 plus 2, that is 3. CD is the missing 9 segment, so we leave it as it is. And DP equals to the square root of 5 units. So in conclusion, 3 equals to square root of 5 units times CD. We divided this equation by square root of 5 units and found out that the missing side CD, it is equal to 3 over square root of 5 units. Then we implemented the Pythagoras theorem on the right blue triangle, triangle CDB. According to the Pythagoras theorem on the right blue triangle, triangle CDB, dB squared equals to DC squared plus CB squared. Okay. Again, dB squared equals to CD squared plus CB squared. So dB equals to the square root of 5. So dB squared is square root of 5 squared, that is 5. Again, dB squared equals to CD squared plus CB squared. dB equals to the square root of 5. So dB squared is square root of 5 squared, that is 5. CD equals to 3 over square root of 5. Therefore CD squared is 9 over 5. Plus CB squared, that is the missing side. So if we're going to found out 5 equals to 9/5 plus CB squared, we subtracted 9/5 from this equation and we found out that 5 minus 9/5 equals to CB squared. Here we multiplied 5 by 5 and then we divided it by 5 in order to have a common factor with this expression. 5 times 5 is 25, so in the numerator we have 25 minus 5, that is 16 over 5. So in conclusion, we found out that CB squared equals to 16 over 5. We took out of this equation and found out that CB equals to the square root of 16, that is 4 over square root of 5. In conclusion, we found out that CB equals to 4 over square root of 5. Now it is very easy to find out the area of this blue white triangle, triangle CDB. It will be equal to the base of the triangle, that is CD, times the height to the base, that is CB, over 2. Thereafter, right blue triangle, triangle CDB equals to the base, that is DC, times the height to the base, that is CB, over 2. DC equals to 3 over square root of 5 units, CB equals to 4 over square root of 5 units, all divided by 2. Here in the numerator we have 3 times 4, that is 12, and the denominator we have square root of 5 times square root of 5, that is 5, times 2. 12 over 2 is 6, so the numerator we left only with 6. And the denominator we left with 5. So in conclusion, we found out that the area of the blue white triangle equals to either 6 over 5 units, or in terms of numbers, it is equal to 1.2 square units. We finished with the first method, then I presented to you how to find out the area of the blue white triangle, triangle DCB, according to the second method. Okay. second method, use all the fields that we have already found out in the first method. We have already found out that AD equals to 1 unit, DO equals to 1 unit, the center of the quarter circle is point O, this angle equals to 90 degrees, and the radius of the quarter circle is OB, that is equal to OA, that is equal to 2 units. Okay, then we completed the quarter circle to a semicircle, and then we extended side CD by a straight line, and according to the first method, we have already proved that when you extend side CD by a straight line, it must touch the circle at point P and only at point P. Okay, so this angle equals to 90 degrees according to the first method. We define this angle as theta, so this angle equals to theta. This angle equals to 90 degrees, so in the right triangle PDO, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle to 180 degrees. Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. So this angle equals to 90 degrees minus theta. So in the right triangle PCB, the right big triangle, this angle equals to theta, this angle equals to 90 degrees. So this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle must be also equal to 90 degrees minus theta in order to complete the sum of the angles in this right triangle to 180 degrees. This angle must be equal to 90 degrees minus theta. Then we proved that the right triangle POD is similar to the right big triangle, triangle PCB. So why those two right triangles are similar to each other? Right triangle POD and the right triangle PCB. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. And finally, this angle is a common angle that belongs to both triangles, so this angle equals to itself. So in conclusion, we found out that all three angles of triangle POD can go into all three angles in the right triangle BCB, therefore those two triangles are similar to each other according to angle similarity rule. Triangle PDO is similar to triangle PBC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that PD over PB equals to DO over CB equals to PO over PC. Here, PD is equal to 5 units, PD is equal to 5 units, PB is 2 plus 2, that is 4, DO is 1, CB is the missing 97, so we leave it as it is. Here, this is CB, and PO equals to 2 units, and PC equals to square root of 5 plus DC. PC equals to square root of 5 plus DC, so in conclusion, square root of 5 over 4 equals to 1 over CB equals to 2 over square root of 5 plus DC. We derive the first equation from this long equation, that square root of 5 over 4 equals to 1 over CB. We cross multiply this equation number 1, and we found out that CB equals to 4 over square root of 5. Here CB equals to 4 over square root of 5, then we implemented the Pythagoras theorem on the right blue triangle, triangle DCB. According to the Pythagoras theorem on the right blue triangle, triangle DCB, DB square equals to DC square plus CB square. In the right triangle DCB, DB square equals to CB square plus DC square. So DB square equals to CB square. CB is 4 over square root of 5, so CB square is 16 over 5 plus DC square. DC is the missing side, so we leave it as it is. DB equals to square root of 5, so DB square is square root of 5 squared, that is 5. So 5 equals to 16 fifths plus DC square. We subtracted 16 fifths from this equation and found out that 5 minus 16 fifths equals to DC square. Here we multiplied 5 by 5 and then we divided by 5 in order to have a common factor of this expression, and found out that 25 minus 16, 5 times 5 is 25, minus 16 over 5. So in the numerator we have 25 minus 16, that is 9, over 5 equals to DC square. So we took a root from this equation and found out that DC equals to square root of 9, that is 3, over square root of 5. So in conclusion, we found out that DC equals to 3 over square root of 5. Now it is very easy to find out the area of this blue right triangle DCB. It is equal to the base of the triangle that is DC times the height to the base that is CB over 2. The area of the blue right triangle DCB equals to the base of the triangle that is DC times the height to the base that is CB over 2. DC is 3 over square root of 5 units times CB that is 4 over square root of 5 units, all divided by 2. Here in the numerator we have 3 times 4 that is 12. In the denominator we have square root of 5 times square root of 5 that is 5 times 2. So here 12 over 2 is 6, so in the numerator we have 6. In the denominator we left only 5. So in conclusion, the area of the right blue triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. So in both methods we got to the same results. Okay, thank you very much.